Good morning, everyone. I'm Mrs.P.HAMEETHA Begam, Assistant Professor of Mathematics, A.D.M. College for Women, NAGAPATTINAM. So, in the previous modules regarding vector calculus and Fourier series, we have seen the differential operator and problems regarding unit normal vector, directional derivative, and problems regarding that. Now, in this module, let us see the formula involving operator del. The vector differential operator del is defined as I dou by dou x plus j vector dou by dou y plus k vector dou by dou z. So, this vector differential operator is also called as Hamiltonian operator. And this operator is used to find the derivative of a vector. Find the derivative of a vector. If a vector is given, we can use operator del to find the derivative of the given vector. Now, let us see the formula involving operator del. Before going into the formula, let us see the preliminary things such as now the del is written as I vector dou by dou x plus j vector dou by dou y plus k vector dou by dou z, which we can shortly written as summation I vector dou by dou x. So, elaborately writing all these three terms, we can shortly write del as summation I vector dou by dou x. Similarly, if phi is a scalar function, we can write del phi as I vector dou phi by dou x plus j vector dou phi by dou y plus k vector dou phi by dou z. And as in the previous equation, we can write this del phi in the short form as summation I vector dou phi by dou x. Instead of writing all these three terms with respect to y and with respect to z, can write shortly as del phi summation I dou phi by dou x. If f be a vector, let f be a vector function, then del dot f vector, which is also called as divergence of vector f vector, which we can write this as summation I vector dou by dou x dot f vector. So, we can write del dot f vector as summation I dou by dou x dot f vector. And again, f vector is a vector function. We can write del cross f vector as del cross product. First we have seen simply del, then the next one phi is a scalar point function and del phi. Next f vector is a vector point function and del dot f, now del cross f. So, we can write this also as curl f vector. Del cross f can also be written as curl f vector, which we can write shortly as summation I dou by dou x cross f vector. So, shortly we can write this terms like this. So, next let us see the formula involving operator del. U and V are scalar point functions then first one is del of u plus v is equal to del u plus del V, and we have to prove the second term del of uv is equal to u del v plus v del u. So first set of formula involving operator del. If u and v are scalar point function, then we have to prove these two property of del, that is del of u plus v. There is no dot product and cross product. Simply del of u plus v, which we have to prove that del u plus del v, and del of uv is equal to u del v plus v del u. So let us see the first proof. Let us take the left hand side, first one, del of u plus v. So del of u plus v, we can write this del as I dou by dou x plus j vector dou by dou y plus k vector dou by dou z of u plus v. So del value here u plus v. Next we have to differentiate. So first we have to insert this u plus v in the first term with respect to x. We have to differentiate that term with respect to x, and then with respect to y, and then with respect to z. So dou of u plus v divided by dou x plus j vector dou of u plus v divided by dou y plus k vector dou of u plus v dou by z. So in the next step, we have to differentiate with respect to x, y, z. So first term will becomes as dou u by, there is addition between u and v. Therefore, first we have to differentiate u with respect to x and then v with respect to y, and in each term similar process is followed. So we get dou u by dou x plus dou v by dou x, and in the second term also we have dou u by dou y plus dou v by dou y, and in the third term we get dou u by dou z plus dou v by dou z. So in each and every coefficient we have two terms, and we can collect those terms with dou u. So we can write separately as I vector dou u by dou x plus j vector dou u by dou y plus k vector dou u by dou z as a separate term, and the remaining, collecting the remaining terms, we get I vector dou v by dou x plus j vector dou v by dou y plus k vector dou v by dou z. So what this term represents means summation I, that is del u. So this value denotes del v, which we have to prove the right hand side. Okay, so del of u plus v, right, left hand side, we started from left hand side and we proved that this del of u plus v is equal to del u plus del v. So first proof is over. Next let us see the second proof. Proof is the left hand side, del of uv, that is del of uv. As uv are scalar point functions, we are not mentioning any vector symbol. So next, as in the previous proof, we have to first differentiate uv with respect to x and then y and then with respect to z. So I dou of uv by dou x plus j vector dou of uv by dou y plus k vector dou of uv by dou z. So the next step, we have to differentiate the terms u into v. As the functions are in the products, we have to use the formula d of uv, that is differentiation of uv in the general formula u v dash plus v u dash. So using that formula we get I vector into u dou v by dou x plus v dou u by dou x. So in each and every term we have to differentiate in a similar manner. So j vector u dou v by dou y plus v dou u by dou y. And the last term becomes k vector u dou v by dou z plus v dou u by dou z. Now we can collect, so totally there are 6 terms. We can collect the terms with the product u's and then v's. So we can take u as a common term and collect the terms, these terms with product u. Therefore, I vector dou v by dou x plus j vector dou v by dou y plus k vector dou v by dou z. So, collecting the remaining 3 terms in the next term, we get v as a common product. So, v into I vector dou u by dou x plus j vector dou u by dou y and k vector dou u by dou z. So, this summation of term represents del v. So, we can write in the next step as u into del v plus v into, this term represents del u. So, we get the right hand side of the second proof, del of uv is equal to u del v plus v del u. So, next let us see the formula involving dot product. So, second set of formula, if u and v are vector point functions and phi a scalar point function, then we can prove del dot u vector plus v vector is equal to del dot u vector plus del dot v vector. The second formula, del dot phi u vector is equal to phi del dot u vector plus del phi dot u vector. And the third one, del dot u vector cross v vector is equal to u v vector dot del cross u vector minus u vector dot del cross v vector. So, the second set of formulae are if u and v are vector point functions and phi a scalar point function, then we can prove these 3 formulae. So, let us see the proof of the first formula. So, del dot u vector plus v vector. So, instead of del we can write I vector dou by dou x, or we can use the short form summation. So, we can use summation I vector dou by dou x instead of del, we are using this one, dot u vector plus v vector. So, in the next step we can bring this dou by dou x, that is the derivative. We have to find the derivative of both u and v. So, we can write the next step as summation I dot dou of u plus v divided by dou x. So, which is equal to summation I vector dot, and differentiating with respect to x, u and v becomes dou u vector by dou x plus dou v vector by dou x. Now, we can bring this summation I with the dot product into the terms, then we get summation I vector dot dou u by dou x plus summation I vector dot dou v by dou x. we can write this as summation I vector dou by dou x dot u vector plus summation I vector dou by dou x dot v vector. And in the next step, we can replace summation I dou by dou x as del dot u vector plus del, we can replace summation I dou by dou x as del here also and dot v vector. Hence we proved del dot u plus v is equal to del dot u vector plus del dot v vector. So hence the first formula is proved. Let us see the next formula, del dot. We have taken two vector point functions, and in the second one we are taking one scalar point function and one vector point function, that is del dot phi u vector. So we have taken the left hand side. Instead of del, we can replace summation I dou by dou x dot phi u vector. So in the next step, we can bring the derivative to the functions, vector and scalar point function. So summation I dot dou phi of u vector by dou x. So which is equal to summation I vector dot, we have to differentiate both phi and u vector. As they are in product, we are using the formula d of uv, that is equal to uv dash plus vu dash. And replacing here, we get phi into dou u by dou x plus u into dou phi by dou x. Now bringing the summation to the terms, both the terms, we get summation. As in the first term, phi is free of summation. We are taking phi as a common term and into summation I dou by dou x dot u vector. So first term is replaced by phi into summation I dou by dou x dot u vector plus summation, and here also we can write summation I dou phi by dou x dot u vector as summation I applicable only for dou phi by dou x. So we are writing like this, and in the next step we can replace summation I dou by dou x by del, then we get phi into del dot u vector, and here we can replace this summation I dou phi by dou x by del phi dot u vector. So we get the right hand side of the second proof, del dot phi u vector, which is equal to phi into del dot u vector plus del phi dot u vector. And next let us see the third formula proof, del dot u vector cross v vector. So we have taken the left hand side of the third formula, del dot u vector cross v vector, and instead of del we are replacing summation I dou by dou x dot u vector cross v vector, which we can write this as in the next step summation I vector dot dou of u vector cross v vector by dou x. Okay. Next summation I vector dot, now we are differentiating this u vector cross v vector. So we get dou u vector by dou x into cross v vector plus u vector cross dou v vector by dou x. So in the next step we are bringing the summation I to the terms inside the bracket. So we have summation I vector dot dou u vector by dou x cross v vector plus summation I vector dot u vector cross dou v by dou x. As here cross product inside the brackets, we have to use one formula, that is, if it is A vector dot B vector cross C vector, we can replace this by A vector cross B vector. The dot and cross may be interchanged. Therefore, we are writing this as A cross B dot C vector. So, dot and cross product may be interchanged. We have one formula like that. And here we are applying this formula to both the terms. So, we get summation I vector cross dou u vector by dou x dot v vector. Okay, so using the formula A dot B cross C, which is equal to A cross B dot C, we are replacing the term like this, and again the second term also we are writing like this, summation I dot, before this step we have to replace the cross product u cross dou v by dou x. As summation I is applicable to dou v by dou x, we can write this as summation I dot minus of dou v by dou x cross u vector. In cross product, if we interchange I cross j, we get the negative sign minus j cross I. Therefore, we are keeping minus here. U cross dou v by dou x is replaced by dou v by minus of dou v by dou x cross u. And in the next step, we can write this as summation I cross dou u by dou x as del cross u vector dot v vector. Okay, and here we can take this minus outside and we can write this summation using the formula A dot B cross C as summation I cross dou v by dou x dot u vector. We can take the minus outside and A dot B is like written as A cross, and this cross is replaced by dot product, and in the next step we can write this as del cross u vector dot v minus this one as del cross, this is v vector dot u vector. So, which is equal to the right hand side of the third formula, and the left hand side is del dot of u cross v, and we proved that del cross u dot v minus del cross v dot u, hence the proof of the third formula. Thank you so much.